Hello everyone, we are here with the same chapter electricity, and this is the part 5th, and the new topic is their parallel combination. In parallel combination, one end of each resistance is connected at one common point, and the other end of each resistance is connected at the other point. We can see here these are the three resistances R1, R2 and R3. Their all the one end are connected to the one point and other ends are connected to the other point. So this is the parallel combination. So we have a proof here. Let three resistors of resistances R1, R2 and R3. This one R1, R2 and R3 are connected in parallel combination. And two end this is here means all the one ends are connected at one end and other ends are connected to the other point. So here all the three are connected in the parallel combination. The current I of the main circuit is divided into three parts. Here this is the battery we have taken. This is a positive terminal, negative terminal, and here we know the conventional current always flow from positive to the negative direction, and the total potential of the battery is V, and current I is there divided into three parts. For R1 resistance it is I1, for R2 I2, and for R3 it is I3. So the current I of the main circuit is divided into three parts. If I1, I2, I3 are the current across R1, R2 and R3 respectively, then I is equals to the algebraic sum of all the currents, means total I current is divided into three parts, I1 plus I2 and I3. Let this is the first equation. But we know that from the Ohm's law, I1 is equals to V upon R1. This is V upon R1. V is the total potential of the battery. I1 is the current in the resistance R1. So here we have taken I1 is equals to V upon R1. I2 is equals to V upon R2, I3 is equals to V upon R3. Let this is whole is the second equation. If Rp is the equivalent resistance, if we see here the equivalent resistance, this whole circuit we have divided into the equivalent resistance. So this is Rp, means all the three when parallelly connected, and we will find the equivalent resistance denoted by Rp. So this is the combination of all the resistance, and this is the equivalent circuit we can say of this parallel combination. If Rp is the equivalent resistance, then I is equals to V upon Rp, where V is the potential difference across AB. This is A and B. This is the potential of the battery. Now from the three equations, first, second and the third equation, what we have that by putting all the values of I is equals to I1, I2 and I3, we will put here I1 and I2 and I3, and I is V upon Rp. So V upon Rp is equals to V upon R1 plus V upon R2 plus V upon R3. If we taking V common from here, the 1 upon R1, 1 upon R2 plus 1 upon R3. V will be cancelled out from the both the sides. So we are having 1 upon Rp is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So what are the characteristics of the parallel combination? The voltage across each resistor is same. As we have seen here in the circuit diagram, the resistance will be, the potential will be same. Second point is there, the reciprocal of all the total resistance is equal to the sum of the reciprocals of all the individual resistances. As we have there, 1 upon Rp is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. The reciprocal of the equivalent resistance is equal to the sum of the reciprocals of all the resistances. So this is the second point. Now the third point is there, the total resistance of the circuit always less than the smallest resistance. In series combination, the total resistance was there always greater than the biggest resistance. So if R1 example is there, if R1 is equals to 2 ohm, R2 is equals to 3 ohm, R3 is equals to 1 ohm. So their parallel combination is the reciprocal of all the sum of the reciprocals of all the resistances. So 1 upon Rp, 1 upon R2, 1 upon 3 plus 1 upon 1. So when taking the LCM, 2 3s are 3 2s are, and here 6, 3 plus 2 5 plus 6 11 upon 6. This is 1 upon Rp. So at last we have to do the reciprocal again. So Rp is equals to 6 upon 11. So we can see here 6 upon 11. Rp is less than 1. So here Rp is the smallest resistance. We can see here this R1, R3 is the smallest here. That is, so Rp is smaller than the smallest resistance. So Rp here is less than 1. So now to get minimum resistance, all resistance must be connected in parallel. This is here. Sometime we have to find the numerical on this page. When numerical is here, a wire of resistance 5 ohm is bent in the form of a closed circuit. What is the effective resistance between the 2 points at the ends of any diameter of the circle? So this is the diameter of the circle. Means this is the wire we have closed. This is a closed circuit in the form of a circle. Here is the point P and this side is point Q. The resistance of wire between 2 points P and Q we have to find at the end of the diameter. This is the diameter here. At the end of the diameter we have 2 points where we have to find the resistance. So if we are having here, this is given here a wire of 5 resistance 5 ohm. Total resistance is 5 ohm is bent in the form of closed circuit. So we are having here diameter. So resistance will be 5 upon 2 ohm. So R1 and R2 will be of 2.45 ohm each. In parallel combination, 1 upon Rp is equals 1 upon R1 plus 1 upon R2. When we will solve this, we get here 1 upon Rp is equals to 2 upon 5. 2 upon 5. So we are having this is 4 upon 5 ohm. Rp is equals to reciprocal 5 upon 4, 1.25 ohm. So we can see here Rp is less than R1 or R2. This kind of numerical we can do. Sometimes we are having the diagrams on the basis of this. Calculate the resistance between P and Q. This is here P and Q. This is the circuit we are having 1, 2, 3, and here is also suppose this is 4, 1, 2, 3, 4 and 5 resistances are here. So we have to find there the equivalent resistance, overall resistance of this circuit. So resistance first we will find in 1 ohm and 2 ohm. They are connected end to end, one end and the other end. So they are connected end to end. It means these two resistances are in series combination. So R1, suppose this is R1 is equals to 1 ohm, R2 is equals to 2 ohm. So their series combination is R1 plus R2. So we are finding here 1 plus 2 is equals to 3 ohm. Now this 3 ohm, we have changed this circuit diagram to this one. So these two resistances are now in series combination and their equivalent resistance is 3 ohm. So this is converted, this 4 ohm as it is, this 3 ohm as it is, this 5 ohm as it is, and these two are converted into the single one and their equivalent resistance is 3 ohm. So this is 3 ohm. Now in this figure we can see here this 3 ohm and 3 ohm both are in parallel connection. So here we have find 1 upon Rp, 1 upon 3 plus 1 upon 3, sum is 2 upon 3. So Rp is equals to 3 upon 2 ohm, or we are having here Rp is equals to, now this total of these two is converted here in 3 by 2 ohm. So this circuit is changes to this one. This is 4 ohm as it is, 5 ohm as it is. The combination of these two is here Rp 3 upon 2. So this is 3 upon 2 ohm. Now these three are connected again in series because they are connected end to end. Here we can see both the ends of the resistance are connected here and other ends are connected at the other point. So these were in parallel combination. Now these three are connected end to end. So it means these three are in the series combination. So here is 4 ohm, 3 by 2 ohm and 5 ohm all are in the series combination. Suppose this is R dash dash. Their algebraic sum is, we'll take the LCM here and we are having this one as total is 2 is the LCM. 2 4 are 8. This becomes 3 and 10. So 8 3 11 plus 10 21 upon 2 10.5. So what is the equivalent resistance? Means the resistance between P and Q is 10.5 ohm. The next numerical is also here. One more is there, so we can reduce our given circuit in the form of the different one. Similarly, the ratio of the two resistance in 5:1. Calculate their individual resistance if they offer an effective resistance of 30 ohm on being connected in parallel. So RP is given. The formula we know that R1 R2